At first glance, centripetal force looks strange. Consider this situation. The moon revolves around the Earth. The moon has a velocity as shown at a particular instant. However, to make this circular motion, the force should be perpendicular to the velocity, as shown. In mechanics, we generally see velocity in the direction of the applied force. Why, then, is centripetal force perpendicular to the velocity? What is centrifugal force? Let's figure it out with an interesting thought experiment. Consider this tennis ball and assume it's moving on a straight line initially. If you apply force perpendicular to its motion for a short time, the object will deflect, as shown. Its direction changes. Now, let's apply the force again, perpendicular to the new direction. The object deflects again. Let's repeat this process. Now, observe the shape the object traveled. It's very close to a circle. If the time interval of applied force is significantly smaller, you will get a more perfect circle. Which means, if an object is always acted upon with a force perpendicular to its velocity, the object will move in a circle. This force is known as centripetal force. One more logical conclusion would be that more the centripetal force, more will the object's deflection, or lesser will be the radius of the circle. This means, for any circular motion to occur, inward perpendicular force must act upon the object. To get the value of the centripetal force, we should approach the problem analytically and start with the way Sir Isaac Newton defined force. However, there's no fun in an analytical derivation, so we'll animate this method. The conceptual understanding we already developed will really help you in science and engineering. Once again, it is clear from this equation that the lesser the radius of the circle, the more centripetal force will be needed. When the moon revolves around the Earth, the gravitational force acting between the moon and the Earth provides the necessary centripetal force. Similarly, when you rotate an object attached to a string, the tension in the string provides the required centripetal force. Consider this spinning wooden block. The frictional force between the block and floor lends the necessary centripetal force. In short, centripetal force should be supplied by some external source such as gravitation, tension, friction, etc. Now that we've learned the concept of centripetal force, the big question is, what is centrifugal force? Consider these examples. When fluid spins in a beaker, as the speed of the beaker increases, the fluid flows outward. Similarly, in this centrifugal casting process, the molten metal always moves to the outer wall. As you increase the speed of this suspended ball, the ball also travels outward. Is there any force called a centrifugal force which is acting radially outward on a rotating object to move it outward? Scientifically speaking, there is no such force as a centrifugal force. It's a pseudo-force. A rotating object always needs a force which is radially inward. Centrifugal force is needed in physics only when you analyze the problem rotating along with the object. In this example, since the observer is sitting inside a rotating cabin, the observer has to add a centrifugal force to analyze the problem. It's a pseudo-force added to convert a non-inertial frame of reference to an inertial frame of reference. If the observer is on the ground, there is no need to use such a force. Now, let's analyze the previous examples using the concept of centripetal force we have developed. As you rotate the ball faster, it moves away. The ball needs a centripetal force. The tension of the rope, more specifically the horizontal component of its tension, provides that force. The tension on the ball has one more responsibility. The vertical component of the tension has to balance the weight of the ball. Logically, as the ball rotates faster, the rope's tension should increase to supply the sufficient centripetal force. However, the weight of the ball does not increase, which means that in order to keep the vertical component of the tension the same, the angle has to increase, like this. This is the reason why the ball moves away as you rotate it faster. The case of the rotating fluid is slightly different. Here again, each fluid particle requires a particular amount of centripetal force to maintain the circular motion. The pressure difference caused by the water level's height disparity generates that centripetal force. The fluid particles at the outer radius obviously need more centripetal force. To satisfy this increasing centripetal force requirement, the fluid surface has to form a curved shape rather than a straight line. When the water volume rotates faster, each particle demands more centripetal force or more pressure difference across the particle. Therefore, the water surface curves more than in the previous case, or you feel like the water is going outward. It's better to avoid using centrifugal force in your scientific or engineering analyses because it's a pseudo-force used only in some special cases. Always work using centripetal force. That's the real force that a rotating object requires.